Hello, this is Professor Michael Smart, and today I'll be giving a short history of scramjet technology. In this presentation, I'll cover four major topics. First of all, I'll discuss the rationale for scramjets and why we would like to develop them. I'll then talk about the application of scramjets, both for cruising at hypersonic speed in the atmosphere and as part of an access to space system where acceleration is required. Next, I'll discuss the development of scramjets since the 1950s, from the time when supersonic combustion was first proved to be possible to the present day when many different scramjet configurations exist. In doing this, I'll highlight particular projects and programs that best characterize the progress that has been made. And finally, I'll talk about some of the scramjet flight programs that have occurred in recent years. So, getting started. What is the rationale for scramjets? Air-breathing propulsion, where air passing through an engine is used as a means of generating thrust, has particular advantages over rockets for sustained hypersonic flight in the atmosphere. In 1964, Antonio Ferri, a well-respected advocate for scramjets, listed the key differences between rockets and air-breathing propulsion as follows. Air breathers have higher specific impulse or fuel efficiency, as they do not have to carry or pump oxidizer. Rockets, however, have a higher thrust to weight. Air breathers must fly within the atmosphere to have large thrust to frontal area, as the air breathing system requires airflow. Now, hypersonic flight within the atmosphere induces high heat loads and drag, but it also allows maneuvering through the use of aerodynamic lift. Given these characteristics, the possible applications of hypersonic air-breathing propulsion are hypersonic aeroplane or cruisers, which fly in the upper atmosphere, or recoverable or reusable space launchers that fly like a plane. Now, here is an artist's impression from the 1960s of what such a hypersonic aeroplane could look like. Now, as you will see as we go forward, our ideas have changed a lot since that time. So what is the potential performance level of a scramjet? Here I have shown a very famous plot of fuel efficiency for different types of aerospace propulsion systems. On the plot in the middle of the figure, on the horizontal axis, I have flight Mach number from 0 up to 16, and then on the vertical axis, we have thrust per fuel use rate, which is essentially the fuel efficiency. At lower speeds, the most fuel efficient system is the gas turbine or the turbojet. However, once you get to Mach 3 or so, materials limitations on the turbine reduce the performance as shown. Between Mach 4 and 6, the ramjet propulsion system is highly performing. These engines do not contain any turbo machinery, but do slow the airflow down to subsonic speed in the combustor. Above Mach 6, the scramjet is the highest performing air-breathing engine. This is because reducing the air velocity to subsonic speeds generates significant losses and extremely high temperatures and pressures. Keeping the airflow supersonic throughout the entire engine minimizes losses and enables net thrust to be generated by a scramjet well into the hypersonic regime. Note that the efficiency of rockets are also shown on the bottom of the figure. Because a rocket must carry both fuel and oxidizer, its propellant-based efficiency is very low. This plot clearly shows the advantage a scramjet can have over a rocket at hypersonic speed. It's the clearest expression of why engineers and scientists have tried to make scramjets a reality from the 1950s to the present day. So let's look into a little more detail on the applications of scramjets. The first application is for a hypersonic cruiser, an example of which is shown in the figure. By a cruiser, we mean a vehicle that is boosted to a certain speed, then spends the majority of the time at constant velocity. An example of this would be an aircraft that flies from Sydney to London in 2 to 3 hours. This type of vehicle would need to fly at speeds up to Mach 8 and also have high lift-to-drag ratio, or L/D. A second application is a scramjet accelerator, such as shown in the second figure. This vehicle could be part of a multi-stage scramjet rocket system for low-cost, reusable access to space. So let's now look at how scramjet technology has developed since the 1950s. Early researchers quickly realized the scientific difficulties of designing scramjet engines. These are the short time available for mixing and ignition of fuel due to the high flow velocity. In fact, a typical residence time for air in a combustor can be as low as 1 millisecond. Secondly, the high surface heat loads generated by hypersonic flight in the atmosphere. These can be greater than those experienced by the space shuttle on re-entry. Thirdly, burning fuel in a duct can sometimes lead to choking or flow blockage, and this must be managed in any practical scramjet. And finally, chemical reactions can freeze in the nozzle expansion, leading to incomplete combustion. As well as these scientific issues, scramjets also have system-level challenges. The most important of these are scramjets don't work below about Mach 4, so another propulsion system is needed to get them up to operational speed. Secondly, scramjets require airframe integration, where the design of the engine and the vehicle are intimately connected, and I'll talk more about this soon. Finally, the nature of scramjet operation changes considerably with Mach number. Therefore, acceleration over a large Mach range is difficult. It was clear in these early days that a significant amount of fundamental research was needed to make scramjets a reality. The historical development of scramjets can be separated into 3 generations. The first generation involved the design of pod-style engines. These scramjets owed considerable heritage to gas turbines, and scramjet pods were developed independent of the vehicle they were meant to propel. The best example of this type of scramjet was the Hypersonic Research Engine, or HRE, which was developed at NASA's Langley Research Center in Virginia between 1964 and 1970. This engine used a large axisymmetric spike for external compression, and its external shape looked distinctly similar to a gas turbine. The HRE used gaseous hydrogen as a fuel and was ground tested at hypersonic speed using a fuel-cooled structure. A significant amount of data on supersonic combustion was collected with this engine. In the final analysis, however, this type of engine was found to be deficient because supersonic combustion could not overcome the external drag of the spike and the pod. Airframe integration was required to reduce the external drag to the level that could be overcome by a scramjet. The second generation of scramjets involved engines designed to integrate smoothly with the vehicle. Here I have shown a sketch of a hypersonic vehicle with an airframe integrated scramjet. The vehicle is long and slender for low drag, and engine modules are mounted side by side on the bottom of the vehicle. But most importantly, the engines are within the vehicle bow shock. So this means that the vehicle is doing some of the compression needed by the engine. In this type of configuration, the external drag of the engines is only a small addition to the vehicle drag. The best way to characterize this type of design is that the vehicle is the engine and the engine is the vehicle. The most famous example of an airframe integrated scramjet powered vehicle is the National Aerospace Plane, or NASP. This vehicle was developed by the United States between 1985 and 1994. Here is an artist's impression of quite an advanced concept developed under NASP. It is clearly based on the ideas of airframe integration. Now, the driving principle behind the NASP program was to bring aircraft-like flexibility to space access. The solution for this was a single stage-to-orbit spaceplane with a combined gas turbine scramjet rocket propulsion system. Some important outcomes of the program were a significant increase in the understanding of scramjets, made possible by high enthalpy ground test facilities, and the birth of modern computational fluid dynamics, or CFD as it's known. As a final analysis of the NASP program, some key points may be made. Firstly, a two-dimensional scramjet flow path was the chosen configuration. However, it involved a significant amount of variable geometry in order to fly to space as a single stage. Secondly, the materials problem of extreme heat loads was never solved. Thirdly, a single stage to orbit vehicle was well beyond the capability of the available technology at that time, and this is still true today. So finally, it became very clear that multi-stage systems, each having a uniquely different propulsion system, is the most practical way to get to space. The third generation of scramjets involves engines with three-dimensional geometry. These new, more complicated designs have evolved in response to limitations observed in the ground testing of 2D scramjets. Over time, it's been realized that two-dimensional geometries may not be optimum for structural efficiency, robust fluid dynamic performance of the engine, or its overall performance. Three-dimensional scramjets that are airframe integrated but include round or elliptical combustors have therefore been developed. With the advent of modern computational methods in the 1990s, many different types of 3D scramjets have been considered. One example of this is the rectangular to elliptical shape transition, or REST scramjet. This configuration was developed at NASA Langley in the late 1990s and includes a rectangular-like capture that enables smooth integration with the vehicle, a rounded combustor shape with elliptical cross-section, and a transition between these two shapes as an integral part of the inlet compression. Some of the advantages of an elliptically shaped combustor are reduced surface area for the same amount of airflow. This can significantly lower both the engine drag and its cooling requirement relative to a rectangular shape. Reduced structural weight due to the inherent strength of rounded structures. And elimination of low momentum corner flows, which can severely limit engine performance. Scramjet engines based on three-dimensional configurations have proliferated in recent times. As an example of this, a complete scramjet based on the REST concept was successfully tested at NASA Langley in 2005. In the final analysis, three-dimensional ideas have opened up the available design space for scramjets. This will hopefully lead to better engines with improved performance. To complete our history of scramjets, let's talk about flight programs. Since the year 2000, there have been a number of scramjet flight tests of increasing complexity. These are HyShot 2, conducted by the University of Queensland in 2002. This payload reached Mach 7.6 and consisted of two partial scramjet flow paths back to back. HYPERX, conducted by NASA in 2004. This was a fully autonomous flight vehicle with a complete scramjet engine that flew at both Mach 7 and Mach 10. And the X-51, conducted by the US Air Force between 2010 and 2013. This was once again a fully autonomous vehicle, and it flew at approximately Mach 5 for a period of more than 200 seconds. Firstly, HyShot 2. The motivations for HyShot 2 were twofold. Firstly, at the time, there had been no known successful scramjet flights that produced supersonic combustion. And secondly, UQ wanted to verify the applicability of results in its T4 ground test facility. The plan was to use a low-cost sounding rocket system to boost a very simple scramjet to approximately Mach 8. The flight payload consisted of two partial scramjets mounted back to back, one being fueled and the other being unfueled. The intake and combustor was designed very conservatively for robust combustion of hydrogen fuel, and a thrust nozzle was not included so that the payload could remain attached to the booster. HyShot 2 took place on July 30, 2002 from the Woomera test range in South Australia. The flight trajectory was highly parabolic, as shown, with the booster reaching approximately 300 km altitude, and the 5-second scramjet test occurred below 35 km on re-entry. On the day, the rocket boost went as planned, and the payload re-entered at Mach 7.6. Good scramjet data was obtained down to approximately 30 km, after which the payload broke up. Here is a plot of pressure along the HyShot combustor for both fuel on and fuel off. The pressure rise shown is from the supersonic combustion of hydrogen fuel. HyShot 2 proved for the first time that supersonic combustion can occur in flight, and it has led to a follow-on joint Australian-US flight program called HyFire. In the wake of all the scramjet development that occurred under the NASP program, NASA decided to conduct a series of flight tests at a range of different Mach numbers. The X-43A flight vehicle was born, and the program became known as HYPERX. The X-43A was a subscale, airframe integrated, scramjet-powered vehicle which had a 2D engine with a movable entrance door, used gaseous hydrogen as a fuel, and was air-launched and then rocket-boosted to the scramjet takeover condition. Flights were conducted at both Mach 7 and Mach 10 in 2004, with the engine operating for approximately 5 seconds. Here is some footage and an animation released by NASA on the flights. Here is the B-52 launch vehicle taxiing at Edwards Air Force Base in California. It has the HYPERX vehicle under its wing. Now the B-52 flew out over the California coast for the launch, and the HYPERX flew out over the Pacific Ocean. Here we see the HYPERX vehicle testing its control surfaces before the flight. And now the control surfaces for the rocket booster. The B-52 is going to drop the stack, and the booster will ignite the HYPERX vehicle up to the scramjet takeover conditions.
Launch. Sequencer reset. Ignition. Guidance on, we are supersonic.
Now we're going to see a view from the stack as the HYPERX is pushed off. Unfortunately, we have no video footage of the Scramjet flight, but the telemetry data showed a smooth operation of the Scramjet and a very successful flight. HyperX was not recovered and splashed down in the ocean. In the final analysis, the HyperX program proved that a Scramjet-powered vehicle could fly. The X-51 flight program was organized in a similar fashion to HyperX, with an air launch and a rocket boost. However, its goals were quite different. Rather than going for a short test at high Mach number, X-51 was aimed at sustained flight using liquid hydrocarbon fuel. Sustained flight requires the use of lightweight materials that can withstand high temperatures. As heat loads increase significantly with Mach number, the modest Mach 5 flight of X-51 simplified materials issues. The free-flying vehicle was powered by a 2D airframe integrated scramjet that did not require a movable door. It was boosted to Mach 4.5 and accelerated to approximately Mach 5. It used liquid hydrocarbon fuel and in the final flight flew for more than 200 seconds. This was a very impressive engineering feat and bodes well for the future of scramjet-powered vehicles. So scramjets have come a long way over the last 60 years, but still have not fulfilled their promise. Maybe some of the students doing this course will be involved in fielding the first operational hypersonic vehicle powered by a scramjet.